All right, we need to find antiderivatives of some function, so let's get some practice. Remember, first of all, that an antiderivative of this function means I need to fill in the blank. The derivative of what is going to give me 3x to the 7th minus 15. Let's rewrite this. What, square root of x? That's x to the 1/2 power. 14 divided by x squared. Let's rewrite that too. Remember what fractional and negative exponents do. So I need to figure out what this is. Now, if you're, really clever, maybe you can just guess and get there. So let's get practice using the power rule. The power rule says that if you're taking the integral of any x raised to any power other than a power of -1, you just add 1 to the exponent and then subtract by that new exponent, and then add any constant. So what we're doing is we really want to find the antiderivative of all of this. We can write antiderivative as an indefinite integral. So this is what we're really doing. We also found out, similar to derivatives, right? If the derivative of, something plus something, we just take the derivatives individually, it's going to be the same thing for antiderivatives. We have a sum and difference rule. I guess this is plus or minus. Just like derivatives. So I'm not going to write this for our future problems, but I'll write it right here. Really, right, what we're taking is the antiderivative of 3x to the 7th. We're subtracting the antiderivative of 15x to the 1/2. Then we're adding antiderivative of 14x to the -2. And again, we also have the constant multiple rule, so this constant could come out in front. Depends on how granular you want to get with the process, but it's just like derivatives. We just need to use the power rule on each one of these. So the power rule for integrals says you add an exponent and then divide by that new exponent. So I add an exponent, 7 goes to 8, and divide by that new exponent. Add an exponent, 1/2 plus 1 is 3/2. Divide by that new exponent. So we need to divide by 3/2. That's the same as multiplying by 2/3. Right, dividing by 3/2, multiplying by 2/3. And then the last one, add an exponent, divide by that exponent. And technically we have 3 different constants that we're adding here. This one has a plus c, this one has a plus c, and this one has a plus c. But 3 constants added to each other is just another constant. So we usually just write one of them. Now all that's left is simplifying. So I didn't really give myself too much room here. So I'll just erase this little comment. What do we have? We have 3/8 x to the 8th power minus, how does this simplify? 15 divided by 3 is just 5. So we have 2 times 5 is 10. And then we're dividing by a -1. That's the same as multiplying by a -1. And x to the -1st power is dividing by x. So this is our antiderivative. There are infinitely many antiderivatives, but so when we say the antiderivative, remember that means the general antiderivative. We could add any constant here and it would still be an antiderivative. That's our answer. And remember, you can always check your answer when you take antiderivatives, because the derivative of our antiderivative should be the original thing. If you wanted, you could take the derivative of our answer if you take the derivative of our answer Again, we use the power rule, bring down the power, subtract power. 3/2 of 10 is 15. Subtract power. This is x to the minus 1 over here. This becomes plus 14 over x squared. And the derivative of a constant is 0. So notice when we take the derivative of our antiderivative, we get the original function. And that's how we can know that we're right. That's the best way of checking your answer for these. Really good habit to be in. And it gives you derivative practice as well. Let's do another one. This antiderivative, I'll try to do this in 2 columns. Well, let's use the rules. This is going to be the antiderivative of e to the x plus the antiderivative of 12 minus 16. Well, let's be consistent. Minus the antiderivative of 16. Let's write this as 16 x to the minus 1. Remember, dividing by x is the same as multiplying by x to the minus 1. That's what negative exponents do. Now we just use our properties. How do we find the antiderivative of an exponential function? Antiderivative of e to the x is just itself. That one's easy. This is just e to the x plus any constant. We'll add the constant at the end. What's the antiderivative of 12? There's no variables here. Do we have something written like that? The antiderivative of any constant is technically the power rule, right? 12 is technically 12 times x to the 0, because x to the 0 is 1. So when we add an exponent and divide by that new exponent, we just get 12x. That's our antiderivative of 12. That's this property right here. The antiderivative of a constant is that constant times x, plus c, of course. So that's exactly what we have here. This is 12x. Again, we already added our constant. And the last one, what's the antiderivative of x to the minus 1? We can't use the power rule here. What happens if we try to use the power rule? If you try to use the power rule on here, add an exponent, divide by that new exponent, so if you forget when you can and can't use it, well, if you accidentally use it, you're going to run into a problem. So we can't use the power rule over here because our exponent's -1. When our exponent's -1, that gives us the natural log of the absolute value. So this is 16 times the natural log of the absolute value of x. And this right here is our antiderivative. We can mostly check the derivative, right? Again, to check our answer, we would take the derivative of our answer, and hopefully we'd get the original function. And yeah, if you take the derivative of this, the derivative of e to the x is e to the x. The derivative of 12x is just 12, right? This is a line. What's the slope of a line? 12 in this case. And then we didn't really talk about the absolute values, so that one's a little weird. It will turn out that this is 16 over x. And then again, the derivative of a constant is 0. There's a long history of these absolute values that we're just going to basically ignore for now because it goes down a theoretical rabbit hole, which is not so important for this applications focused class. But again, look, we took the derivative of our antiderivative. Whole idea is derivative and antiderivatives are like the backwards of each other. They undo each other. Took the derivative of our antiderivative and we got the original function. That's how we know that we're right. Last example here. Let's spice things up, okay? Find a function so that its derivative is e to the x and its value is 10. So let's do this question in two parts. First, let's do this red part. Find f of x so that its derivative is e to the x. The derivative of what function equals e to the x? Oh, this is a question asking about antiderivatives. We know what goes in here. So you could just write down what the answer is, or you could say we're looking for the antiderivative of e to the x and use our formula that tells us that this is e to the x plus c. There are infinitely many antiderivatives with a derivative of e to the x. So there are infinitely many answers to this red part. But we also have this blue requirement. Oh, so we need to pick one, right? There are infinitely many of these. This is our f of x. We need to find the f of x with this blue property. So what is f of 0? That'll be e to the 0 plus our constant. Now we said f of 0 needs to be 10. What is e raised to the 0th power? 1. Any number to the 0th power is 1. Outside of 0. 0 to the 0th power is something weird. Well, we can find our constant. Let's subtract 1 from both sides. Our constant must be 9. You might have thought it was 10, but it's actually 9. So our answer is that our function is e to the x plus a constant, and we specifically found that the constant that we wanted is 9. This is what's known as an initial value problem, and is very, very common in like higher level math and differential equations and stuff like that. We have a requirement about a derivative. We have a requirement about the original function. We put those together to get one specific function. And you could check your answer, because if you took the derivative, you would get e to the x. And if you check this condition, you'll get 10. So that's how we can know this is our answer. Let me know if you have questions about any of these problems, and we will have some more fun fundamental theorem of calculus in the next video.